For hundreds of thousands of years after the Big Bang, there was no light as we know it. Infant universe was a thick, hot fog of plasma of protons, electrons, and photons, all locked together in a radiant soup. Photons, the very particles of light, did exist, but they were trapped. Every time they tried to move, they were instantly scattered by charged particles. Imagine a cosmos that's incredibly bright on the inside, but completely hidden from itself. A universe without transparency. This wasn't a dark age because light didn't exist, but because it couldn't escape. In those early eons, the universe was blind. Then, about 380,000 years after the Big Bang, everything changed. The universe expanded and cooled to a temperature of around 3,000 Kelvin. This was just cool enough for electrons and protons to finally pair up and form neutral hydrogen atoms. This event, which scientists call recombination, was a turning point. Suddenly freed from the constant pinball game of scattering, photons began to travel unimpeded through space. This was the moment light truly broke free. As these photons journeyed across the cosmos, they stretched, cooled, and spread out, creating what we can still detect today, the cosmic microwave background, or CMB, no matter which direction we look in the sky. That faint, ancient glow remains a whisper from the dawn of time. But even after this great release, the universe was still incredibly dim. The light from recombination was uniform and fading. There were no stars, no galaxies. It's just a vast, cool, and dark expanse, filled with invisible hydrogen gas. So where did the first true light, the brilliant light of stars, come from? The answer, as it so often is in cosmology, is gravity. Over millions of years, tiny, almost imperceptible fluctuations in the density of matter quantum ripples from the very first moments of creation began to grow. Regions that were just slightly denser than their surroundings started to pull in more and more matter. These gravitational seeds grew into the first cosmic clouds, which then collapsed into protostars. When gravity's immense pressure squeezed those primordial clouds tight enough to ignite nuclear fusion in their cores, the first stars were born. They burst into existence like cosmic torches, shining into the primordial darkness. This era, known as cosmic reionization, marked the universe's final transition from an opaque fog to the luminous cosmos we know today. It was the ultimate triumph of light over shadow. These first stars were nothing like our sun. They were true monsters, hundreds of times more massive, burning incredibly hot and living fast, spectacular lives. Their light was so intense and powerful that it literally tore apart the neutral hydrogen atoms that filled the space around them, stripping away their electrons and turning vast regions of the universe transparent once again. The cosmic fog finally lifted for good. The cosmos lit up. But this was more than just simple illumination. This was the beginning of structure, of definition, of contrast. It was the very beginning of form itself. Because light doesn't just reveal the universe, it actively shapes it. From this point forward, two great sculptors would begin a cosmic dance that continues to this day. Light, which expands, radiates, and reveals. And gravity, which pulls inward, gathers, and conceals. The interplay between these two fundamental forces would go on to create every single cosmic object we know and love, from brilliant, glowing nebulae to the vast, empty voids between galaxies, from radiant stars burning for billions of years to the ultimate shadows of existence, black holes. And so began the eternal battle, not of good versus evil, but of energy versus entropy, of illumination versus collapse. It says this delicate and dynamic balance that gives rise to all the cosmic beauty we see around us. Think about it. Every single photon of light that reaches your eye is a survivor. It's a tiny traveler that has journeyed across unimaginable distances, escaped gravity's relentless pull, avoided being absorbed by dust and gas, and carried its information across time itself, just to end its journey with you. But every shadow you see is just as real and just as important. It's evidence of where light was stopped, bent, or completely devoured. The universe isn't purely one or the other. It is built in the space between them, the tension, the dialogue, the epic and beautiful battle between light and shadow. Before there was light, there was darkness. A silence older than time, a cosmic canvas just waiting for the first brushstroke of creation. And then, in a single silent explosion, it happened. Light erupted into existence. Photons, the tiny messengers of energy, flooded the void, screaming the birth of the visible universe. But from that very first moment, the cosmos has lived in a state of constant tension. A cosmic tug-of-war between the brilliant force of expansion and the crushing pull of gravity, between the spark of illumination and the infinite draw of the abyss. This is the story of light and shadow, not just as ideas, but as fundamental physical realities. These are the forces that define the structure, the life, and the ultimate fate of everything that has ever existed, and everything that ever will. Light is so much more than what our eyes can see. It's the language of the universe itself. A vast spectrum of energy stretching from the most powerful gamma rays to the longest radio waves. Each frequency is like a different voice in a grand cosmic choir, telling a story about its origin. Shadow, on the other hand, isn't just the absence of light. It's what happens when matter stands up and challenges illumination. It's the effect of gravity bending, blocking, or even consuming the very photons that reveal reality to us. Think about it. Every galaxy, every star-forming nebula, every mysterious black hole, even life itself exists right at this intersection, on the delicate borderland between brightness and darkness. But to truly understand why this struggle defines everything, we have to travel back in time, all the way back to the very first light ever born. This first light, known as the cosmic microwave background, is the afterglow of creation, a faint echo of the Big Bang. For 380,000 years after the universe began, was a superheated, opaque fog of plasma. Light was trapped, constantly bouncing off free-roaming electrons, unable to travel freely. The universe was bright, but it had no form, no structure. It was a brilliant, featureless chaos. Then, as the universe expanded and cooled, atoms began to form. Electrons were captured into orbits, and for the first time light broke free. This moment, called recombination, is when the universe became transparent. The first shadows were cast as vast clouds of hydrogen gas began to clump together, blocking the ancient light. These weren't just shadows, they were the seeds of everything we see today. Within these primordial shadows, gravity went to work. The slight variations in density, the tiny pockets of darkness, began to pull in more and more matter. These were the cosmic nurseries where the first stars would ignite. Imagine, after millions of years of expanding darkness, the first star flickers to life. A brilliant pinprick of fusion pushing back against the shadows that gave it birth. This was a turning point. Stars are the great engines of light, forging heavier elements in their cores and bathing their surroundings in radiation. But even they are locked in this cosmic battle. A star's life is a constant balancing act between the outward pressure of the light it creates and the inward crush of its own gravity. When a massive star dies, gravity finally wins. It collapses in on itself with such force that not even light can escape, creating the ultimate shadow, a black hole. Black holes are the universe's apex predators of light. Their gravitational pull is so immense that they create a region of space, the event horizon, from which nothing can return. They are the physical embodiment of shadow, bending space-time and consuming stars, gas, and light itself. Yet even here, the story isn't so simple. Around these abysses of darkness, we find some of the brightest objects in the universe: quasars. As matter is pulled toward a supermassive black hole at the center of a galaxy, it forms an accretion disk that heats up to incredible temperatures, shining brighter than 1 trillion stars. The ultimate paradox. The darkest objects in the cosmos are responsible for creating the most brilliant beacons of light. This dance between creation and annihilation, light and shadow, happens on every scale, shaping galaxies and dictating the fate of the universe. From the sunlight that fuels life on Earth to the dark voids between galactic superclusters, this eternal battle is the engine of cosmic evolution. It's not a story of good versus evil, but a fundamental process of balance, a struggle that gives the universe its magnificent structure and its profound beauty. Every shape, every shimmer we see across the cosmos, from the swirling arms of galaxies to the faint haze of starlight, is carved by an ongoing war between radiance and gravity. Here, light sculpts the visible universe, while darkness molds the invisible one. In this video, we step into the gallery of cosmic sculptors' nebulae, black holes, and the countless shadows and illuminations that define the architecture of reality itself. A nebula is both a cradle and a grave. It is where stars are born, and where they return after death. These vast clouds of dust and gas, stretching for light years, are the canvases upon which light paints its masterpieces. But nebulae would be invisible without illumination. When newborn stars ignite within them, their ultraviolet light ionizes the surrounding hydrogen, causing it to glow, a process known as fluorescence, but on a cosmic scale. That's why we see those brilliant red, blue, and green hues in places like the Orion Nebula. It's the light of elemental gases being energized, with each color revealing a different composition. Here, the battle between light and darkness takes a beautiful turn. Stars are sculpted by the very shadows they illuminate. The darker regions, those intricate tendrils, and voids are dense knots of dust, shielding the inner regions from radiation. Inside them, gravity relentlessly compresses material, forming new stars. Light doesn't simply reveal nebulae. It creates contrast, which is the language of structure. Without darkness, no form could exist. Without illumination, no form could be perceived. Let's look at the pillars of creation. In visible light, they appear as colossal silhouette columns of darkness against a glowing backdrop. But in infrared, we see inside them tiny, bright stars being born in the shadows. It's a powerful truth. The cosmos hides its beginnings within its darkness. Even creation needs concealment. But if nebulae are the wombs of light, black holes are its devourers. They are regions where gravity becomes so intense that space and time themselves curve inward, a gravitational abyss from which even photons cannot escape. To understand black holes is to confront the very limit of light's existence. At the event horizon, the boundary around a black hole, the escape velocity equals the speed of light. Beyond it, light is no longer free. It falls inward, frozen in time from our perspective. In this realm, light doesn't simply vanish, it's transformed. Some of it spirals around the black hole, creating a luminous ring called the photon sphere. Some is redirected by the warping of spacetime, producing the surreal gravitational lensing that allows us to see the same object from multiple directions. This strange bending where light becomes an obedient servant to gravity is how black holes cast gravitational shadows. When the Event Horizon Telescope captured the first image of a black hole in 2019, what we saw wasn't the hole itself, but its absence of light, a circular void framed by an incandescent halo of falling matter. It was a portrait of the cosmic battlefield made visible. That glowing ring was light at its most defiant, orbiting the threshold of eternity. And the shadow within was gravity's final victory, the point where illumination ends. Yet even this victory isn't total. When black holes consume matter, they also unleash jets of light, streams of high-energy radiation shot out at near-light speeds from their poles. These jets can extend for thousands of light years, igniting surrounding gas and shaping entire galaxies. The irony is profound. Even the darkest objects in the universe cannot escape illuminating it. From the vast scales of galaxies, we come to something familiar and deeply symbolic: an eclipse. An eclipse is nature's reminder that light and shadow are not enemies, but partners in motion. When the moon passes between Earth and the sun, it creates one of the most awe-inspiring events visible from our planet: the sudden day-turn-night. When the corona of the sun blazes from behind the lunar shadow, it's a moment that has inspired myths for millennia: dragons devouring the sun, gods fighting in the heavens. But behind those stories lies a perfect alignment, a geometric coincidence almost too elegant to be random. The moon is 400 times smaller than the sun, but it's also 400 times closer to Earth, making their apparent sizes equal in our sky. That symmetry allows total eclipses to exist at all. It's a delicate balance, a visible echo of the universe's ongoing equilibrium between brightness and concealment. During an eclipse, we see something few ever notice: the light of the sun's atmosphere, which is invisible under normal conditions. For a few precious moments, the veil of brightness is lifted, and we witness the sun's hidden structure, its magnetic tendrils and plasma loops, shimmering like living fire. The eclipse is more than a spectacle. It's a microcosm of a cosmic truth. Sometimes, to see the full complexity of light, darkness must intervene. Everywhere we look, the universe maintains a fragile equilibrium between revelation and concealment. Galaxies are luminous islands, yet most of their matter is dark and visible to all wavelengths of light. Even our sun radiates less than a billionth of its total energy toward Earth. The rest is lost to the void. Light expands, gravity confines, light radiates information, darkness protects it. Without this balance, there would be no stars, no shadows, and no observers to notice either. In the grand scheme, light and darkness are not opposites. They are interdependent. Each defines the other, sustains the other, and in their eternal dance, they build the universe. We think of darkness as an absence, the emptiness left when light fades. But in the cosmos, darkness is not nothing. It is structure. It is substance. It is force. Invisible to our eyes and undetectable by our most sensitive telescopes, dark matter and dark energy dominate the universe. Together, they make up more than 95% of all cosmic content. The light, the stars, galaxies, and everything we can see is only a thin veneer floating atop an ocean of shadow. This is not a metaphor. It's physics. In the 1970s, astronomers like the brilliant Vera Rubin began measuring how galaxies rotated. Now, according to everything we knew from Newton's laws, stars, farther from a galaxy's center, should orbit more slowly, just like how Pluto moves much slower than Mercury around our sun. But they didn't. The outer stars were moving shockingly fast, so fast that based on all the visible matter, the galaxies should have torn themselves apart, flinging stars into the void. Something unseen was holding them together. That something became known as dark matter. This mysterious substance doesn't emit or reflect light. It doesn't absorb radiation. We can't point a telescope at it and see anything at all, yet it exerts gravity. While we can't see dark matter directly, we can map its influence, just as you can trace the path of the wind by watching the trees sway. One of the most powerful tools for this comes from Einstein himself. His theory of general relativity revealed that mass curves space-time, bending light as it travels. Astronomers use this principle, called gravitational lensing, to see invisible mass. When light from distant galaxies passes through regions filled with dark matter, that light gets bent and magnified, revealing the cosmic silhouette of the unseen. It's like looking at the distorted reflection in a funhouse mirror to figure out the mirror S-shape. These observations show us that dark matter forms massive invisible halos that extend far beyond the visible edges of galaxies. These halos are linked together into immense cosmic filaments, creating a vast, invisible scaffolding for the entire universe. The truth is, without dark matter, there would be no galaxies, no stars, and no structures for light to illuminate. Darkness, it turns out, gives light its stage. But there is another, even stranger darkness. While dark matter pulls galaxies together, something else is pushing them apart. In 1998, two separate teams of astronomers were studying distant supernovae exploding stars to measure the expansion of the universe. Everyone expected to find that gravity was slowing the expansion down. Instead, they made a shocking discovery. The expansion was accelerating. Something, an unknown energy permeating all of space, was driving galaxies away from each other, faster and faster over time. We call this force dark energy. If dark matter is the hidden skeleton of the cosmos, dark energy is the invisible breath expanding its lungs. It's not dark in the sense that it's black, but in the sense that it is a complete mystery of force we cannot perceive or define. It's fascinating because Einstein once introduced a cosmological constant into his equations to try and keep the universe static, which was the prevailing idea at the time. He later famously called it his greatest blunder. Yet today, that same mathematical concept might be our best description of dark energy's repulsive pressure, the relentless push that will determine the universe's ultimate fate. We still don't know what dark energy truly is. It could be the inherent energy of empty space, what's known as vacuum energy. Or it could point to an entirely new field of physics we haven't even dreamed of. But one thing is clear. Light may reveal the cosmos, but darkness rules its destiny. So, could this darkness be even more fundamental than just missing light? Modern physics suggests that the vacuum, what we call empty space, is anything but empty. It teems with unseen energy, a restless sea of virtual particles popping in and out of existence. The fabric of space-time itself vibrates with potential, even where no light travels. In this sense, darkness isn't the absence of light, but the ground state of reality, the lowest possible energy, cosmic baseline from which all illumination emerges. Think about it. In quantum theory, light isn't born from nothing. It arises from transitions, from changes between energy states. Without the possibility of an unlit, lower energy state without darkness, there could be no emission, no light at all. So perhaps the Big Bang wasn't an explosion of light into a void of nothingness, but rather the awakening of contrast, the very beginning of the difference between what shines and what does not. This leads us to a profound paradox of perception. Our entire human experience of the cosmos is filtered through vision, through light. We evolved under a sun that defines our reality of day and night, of existence and void. But the truth of the universe completely transcends our vision. We are creatures of photons, living in a universe built on shadow. Every telescope ever made, from Galileo's first crude refractor to the incredible James Webb Space Telescope, captures only the luminous surface of reality, that tiny 5%. The rest, the grand machinery operating beneath it all, remains cloaked in darkness. And so, the question deepens. Is the universe truly dominated by darkness? Or are we simply blind to most of its light? Perhaps in a way both answers are true. It seems the universe is a story of balance. Every photon that escapes a star's gravity is a victory for light. Every galaxy that holds itself together against the chaos of space owes its very structure to darkness. Neither can truly exist without the other. From the faint afterglow of the Big Bang, the cosmic microwave background, to the simple flicker of a candle here on Earth, every single instance of light arises within a sea of invisible forces, is shaped, confined, and ultimately defined by the shadow that surrounds it. Perhaps light and darkness aren't two opposing sides of a coin, but a single, fundamental process, the way the universe expresses contrast and creates information. Creation itself may be the act of separation, the moment light steps out of the shadow, and in doing so, gives both itself and the darkness a profound and beautiful meaning. From a cosmic perspective, our world is a vibrant oasis of light, a delicate layer of life, clinging to a small planet, orbiting an ordinary middle-aged star. Yet even here, the eternal dance between illumination and shadow defines everything. It sets the rhythm of our days, steers the course of evolution, sparks the miracle of photosynthesis, and even ignites the dawn of reason itself. For humanity, light isn't just a physical phenomenon. It's existential. It nourishes our world, guides our senses, and symbolizes our quest for understanding. But wherever light shines, a shadow is cast, shaping our perception, our perspective, and the mysteries that lie just beyond our sight. This is the story of how light and shadow sculpted not just our planet, but the very cradle of life and thought. Every heartbeat, every breath, every molecule of oxygen you inhale it, all traces back to photons journeying from our sun. Deep within its core, hydrogen atoms fuse into helium, unleashing a torrent of energy as light and heat, a process that has continued for 4.6 billion years. Only a tiny fraction of that light ever reaches Earth, yet it's more than enough to sustain an entire biosphere. When sunlight touches a leaf, chlorophyll molecules capture those photons, converting their energy into chemical bonds. This ancient process, photosynthesis, is how light literally became life. Plants transform sunlight into sugars, fueling entire ecosystems, producing the oxygen we breathe, and laying the foundation for all complex biology. Without it, Earth would be a cold, dark, and silent world. But there's more. Sunlight also governs our climate, weather, and the very cycles of time. The 23.5-degree tilt of Earth's axis creates our seasons, alternating periods of warmth and shade that drive migrations and biological rhythms. Every living thing on this planet evolved under these conditions, the constant give and take between brightness and its absence. In this way, light, by its very presence, creates time. The daily rotation of our planet carved the first calendars into the minds of our ancestors. Civilizations rose and fell in harmony with the sun, sowing, harvesting, worshipping, and building according to its predictable patterns. In ancient Egypt, the sun was Ra, the ultimate giver of order. In the Americas, the Inca emperor was revered as the child of the sun. In nearly every culture, light became synonymous with creation, vision, and truth, while darkness represented mystery, the vast domain of the unknown. And yet, the night was also a profound teacher. When daylight faded, early humans looked up and saw infinity. The darkness, the stars appeared, offering us our first true glimpse of the vastness beyond Earth. Paradoxically, it was shadow that expanded our vision. By studying the movement of stars and the phases of the moon, humanity discovered geometry, navigation, and the great cosmic cycles. Every early observatory, from Stonehenge to the pyramids, was built not just to honor light but to measure shadow, because shadow is how we perceive time. A sundial, after all, doesn't measure light, it measures its absence. Its moving shadow traces the sun's journey, translating cosmic order into human understanding. From this beautiful interplay, science was born. The ancient astronomers, philosophers, and later physicists wrestled with the same fundamental question. Why does light behave the way it does? Why does it travel in straight lines, bend through glass, or split into a rainbow of colors? To find answers, they built instruments designed to capture and constrain its lenses. Prisms and cameras, tools that masterfully turned light into knowledge. When Isaac Newton passed sunlight through a prism in the 1660s, he didn't just shatter a beam of light, he shattered a long-held assumption. Light wasn't pure, it was a composite of colors, different wavelengths that could be separated and recombined. Centuries later, James Clerk Maxwell unified electricity, magnetism, and light into a single elegant set of equations, revealing light as an electromagnetic wave. Then, Albert Einstein unveiled light's baffling dual nature. It behaves as both a particle and a wave, a quantum paradox as profound as the universe itself. Every step we took deeper into the study of light revealed that illumination itself hides its own mysteries. Each photon carries not just energy, but information about the temperature of distant stars, the motion of galaxies, even the age of the universe. Light became the ultimate messenger. And yet, the more light reveals, the more shadow it casts. The more precisely we understand illumination, the more profoundly we realize how much remains unseen. From the dark energy expanding the cosmos to the unlit dimensions of space-time, it seems that knowledge itself obeys the same law. Each new discovery casts a new shadow of unanswered questions. But light doesn't just sustain our biology or fuel our technology. It shapes our emotions, our art, and our search for meaning. Painters like Caravaggio and Rembrandt mastered chiaroscuro, the dramatic contrast between light and dark, not to depict a literal scene, but to capture the very drama of human existence. Photographers, architects, and filmmakers all use shadow to define depth. Because without darkness, light has no form, no direction. Even our own psychology is tethered to this rhythm. Our circadian cycles, our moods, and our alertness all follow the patterns of light. Prolonged darkness can lead to despair, yet total, unceasing illumination can overwhelm our senses. Life, it seems, thrives in contrast and balance. The spread of artificial light across the globe has given us the incredible power to turn night into day, but it has come at a cost. The disappearance of true darkness has hidden the stars from more than half of humanity. In many cities, the Milky Way is now just a memory, the cosmos itself veiled by our own brilliance. Shadow is not our enemy. It is a vital part of the equilibrium that allows us to perceive the universe and ourselves with clarity. Our civilizations have become beacons in the night. To any distant observer, Earth now glows with artificial light, a planetary signature of intelligence. Radio waves, television broadcasts, and laser signals all are human-made photons streaming into the void. We've learned to use light not just to see, but to communicate. Fiber optic cables carry the world's data through threads of glass at nearly the speed of light. Lasers measure the distance to the moon with astonishing precision. And our spacecraft, like Voyager 1, send faint signals across billions of kilometers each. Photon, a whisper of consciousness carried across the cosmic darkness. For the first time in the history of the universe, light itself is carrying knowledge, deliberately shaped and sent by thought. It is the moment when the universe, through us, became aware of its own illumination. Here on Earth, light is life. But its deeper gift is understanding the power to reveal the hidden order of things. And yet to see clearly, we must also honor the shadow, for without it, we lose the very contrast that makes sight possible. Every sunrise reminds us that the dance between light and darkness is not a battle to be won. It's a delicate balance to be maintained. Still, the question remains, how did we truly uncover the scientific truth of light and shadow? How do we journey from myth to measurement, from worship to physics? The answer lies in the incredible story of discovery itself. Journey across centuries, fueled by curiosity, mathematics, and our relentless pursuit of illumination. The quest to understand light is one of humanity's oldest obsessions, a story stretching from the temples of antiquity to the laboratories orbiting Earth. It is the thread that connects myth to mathematics, religion to relativity. Light has guided our eyes, powered our civilizations, and ultimately revealed the structure of the cosmos. But our understanding of it did not come easily. It evolved through centuries of observation, argument, and revolution as humans learned not just to see, but to measure seeing itself. The ancient Egyptians, light was divine, the visible presence of the sun god Ra. To the Greeks, it was a mystery of geometry and thought. Empedocles believed that light emanated from the eye, that vision occurred because the soul sent rays outward to touch the world. Then came Euclid, who described light's straight-line behavior in optica, laying the first mathematical foundation for geometrical optics. But centuries later, Al-Hasan, a scholar of the Islamic Golden Age, overturned that belief. In the 11th century, in his book of optics, he demonstrated that light travels into the eye, not from it. Using lenses, mirrors, and darkened chambers, Al-Hasan founded the experimental method that would become modern science. He showed that perception depended not on mystical emanations, but on the physics of illumination, a profound shift from philosophy to empiricism. From then on, light would no longer be the domain of gods, but of laws. When Isaac Newton performed his prism experiment, he shattered centuries of assumptions about purity and perfection. Sunlight, once seen as divine and immaculate, was revealed to be composite, a blend of many wavelengths, each bent by a different angle. This discovery laid the foundation of spectroscopy, the science of analyzing light to understand the universe. Newton's insight went beyond optics, recognized that color was not a property of objects, but of light itself, a concept that would redefine art, perception, and physics. Through light, Newton glimpsed order, a hidden mathematical symmetry, connecting nature's beauty to universal law. For over a century, scientists debated what light truly was, a stream of particles or a continuous wave. In 1801, Thomas Young conducted an experiment that changed everything. He passed light through to narrow slits and observed an interference pattern alternating bright and dark bands. The result was undeniable. Light behaved like a wave. This discovery unified optics with the broader world of vibration and resonance, connecting light to sound, water, and energy itself. Later, James Clerk Maxwell would bring the revolution to completion. His 19th century equations showed that electricity and magnetism were two sides of the same phenomenon, and that light was their union, an electromagnetic wave propagating through space at a constant speed. That constant, the speed of light, or c, became the most sacred number in physics. It was not merely a property of illumination, it was the fundamental limit of reality. Then came the early 20th century, and with it, the realization that even Maxwell's triumph was incomplete. Einstein's study of the photoelectric effect revealed that light also behaved as discrete particles, photons, each carrying a quantum of energy. This duality, wave and particle coexisting in one phenomenon, shattered classical intuition. Einstein's insight earned him the Nobel Prize and birthed quantum theory, a framework that would redefine reality itself. But the paradox deepened. In experiments, light sometimes acted like a particle, a localized burst of energy. Other times, it behaved like a wave, spreading and interfering with itself. It wasn't just light that was strange, it was nature. And the line between energy and matter, illumination and form, began to blur. For most of history, humans saw only a narrow band of the electromagnetic spectrum, the small window of wavelengths visible to our eyes. But as our technology advanced, so too did our sight. We built instruments to capture radiation beyond human vision: radio, infrared, ultraviolet, X-rays, and gamma rays. Each revealed a new face of the universe. Radio telescopes unveiled cosmic structure and cold hydrogen clouds. Infrared sensors peered through dust to watch stars being born. Ultraviolet and X-ray observatories showed the violence of black holes and supernova. Gamma ray detectors recorded the most energetic events in existence, the universe's true cataclysms. With every expansion of the spectrum, darkness retreated a little more, yet never entirely, because each discovery only revealed how much more lay hidden. The invisible became not a void but a frontier. By studying how light bends, fades, and shifts, scientists began to map even what light cannot show. Through gravitational lensing, they traced the presence of dark matter. Through redshift, they measured the expansion of the universe. Through cosmic microwave background radiation, they glimpsed the universe's infancy. Light became the universe's historian, carrying within it the record of every collision, fusion, and explosion since time began. But there's an irony here. All our knowledge of darkness comes from light. Even the concept of a shadow depends on the detection of photons, their absence as much as their presence. In studying illumination, we have learned to see the unseen. Science has turned photons into probes, shadows into data, and the void itself into a readable language. Today, light is no longer just observed, it's engineered. Lasers, invented in 1960, harness coherent photons to perform tasks once thought impossible: surgery at microscopic precision, communication through fiber optics, measurement of gravitational waves. In the quantum age, we even manipulate single photons, using them to encrypt information or simulate universes in miniature. Every device, every screen, every digital image is a form of controlled illumination. Human-crafted light bending to our will. And yet, as we learn to command light, we approach a cosmic irony. We can create brilliance brighter than stars. Yet we cannot escape the darkness that surrounds it. Even our brightest achievements remain specks of radiance in an infinite night. The scientific journey of light is the story of civilization itself, from survival to understanding, from vision to revelation. Each era expanded our range of perception, and with it, our awareness of how much remains hidden. For all our progress, the cosmic duel continues, not only in the heavens, but in our own pursuit of truth. Because science, like light, expands outward, revealing, while mystery, like shadow, deepens with every step. Every dawn implies a dusk. For the universe, too, the story of light is not eternal. It began in a flash, the Big Bang's radiant surge, and it will end in silence. The cosmic battle between light and shadow is not just symbolic. It is the destiny of all creation. In the end, gravity and entropy will claim victory, not with a bang, but with a slow, silent dimming. The universe today is roughly 13.8 billion years old, still a teenager in cosmic terms. For now, galaxies shimmer with the combined light of trillions of stars, but already the darkness is gaining ground. Massive stars live fast and die violently, burning out their fuel in just a few million years. Smaller stars like our sun burn for billions of years, and the tiniest red dwarfs, dim and stubborn, may endure for trillions. Yet all are temporary. As hydrogen, the universe's most abundant fuel, dwindles, so too will the fire of the cosmos. In the coming tens of trillions of years, one by one, the stars will go out. Galaxies will lose their glittering hearts. The night sky, once brilliant with cosmic flame, will become sparse, then completely black. This era, the degenerate age, will mark the universe's transition from radiance to ruin. When stars like our sun die, they leave behind white dwarfs, small, dense cores no larger than Earth, but containing half a star's mass. These stellar remnants will glow faintly for billions of years, gradually cooling into black dwarfs, cold, invisible spheres drifting through the darkness. But here's a haunting thought. No black dwarf yet exists. The universe is simply not old enough for even one to have fully cooled. They are relics of a future we can only predict, a time when light itself will have faded below detectability. Every beam, every photon, will have stretched into near non-existence, diluted by the universe's endless expansion. When that time comes, Darkness will no longer be the absence of light, it will be the only state left. Even as stars die, black holes endure. They are the ultimate victors of gravity, the engines of darkness that consume the very light that defines them. In the far future, galaxies will be ruled not by stars, but by black holes. Supermassive ones, billions of times the mass of our sun, will devour the remnants of their galaxies, feeding on dust, gas, and even entire solar systems. But even these titans are not eternal. Through a process called Hawking radiation, black holes slowly leak energy, evaporating over unimaginable timescales. The last black holes will vanish after roughly 10 to the power of 100 years, a number so vast it defies comprehension. When they do, they will release their final photons, faint whispers of energy echoing into an otherwise absolute void. That moment will mark the end of light as a physical phenomenon. After the last black hole fades, no light will remain, no stars, no warmth, no movement. The universe will become a sea of subatomic particles drifting through infinite cold, what cosmologists call the heat death or the big freeze. In that far future, the temperature of the cosmos will approach absolute zero. All energy will be evenly distributed. No gradients will remain to power change, no difference to generate structure. Entropy, the measure of disorder, will reach its maximum. The universe will be perfectly balanced and perfectly dead. Light, once the symbol of creation, will have surrendered entirely to shadow. For as long as humans have looked upward, light has been our metaphor for knowledge, for spirit, for life itself. But the universe reminds us that light is temporary, that even illumination is part of a cycle, a sense. Darkness isn't evil, nor is it defeat. It is the quiet end of motion, the inevitable balance after creation's expansion. Just as stars are born from the collapse of cosmic clouds, perhaps new universes could one day emerge from the collapse of this one, reigniting the flame in a new cosmic dawn. Perhaps this isn't a final shadow, but merely a pause and interval between breaths in an infinite cycle of light and dark. Even if the cosmos itself grows cold, the light it once produced has already changed everything. It forged atoms, grew galaxies, and allowed life to awaken and to wonder. Every thought you've ever had, every story, every discovery, all are powered by photons born from ancient stars. We are beings made of darkness that learn to see. And for a brief, beautiful moment in cosmic time, we have illuminated the universe right back. Our telescopes, our knowledge, our imagination, they are all extensions of that same cosmic light. Even when the stars are gone, their memory will live on in the patterns of the universe, in the mathematics that once described their glow. Light is not eternal, but neither is shadow absolute. Both are halves of a single whole, the cycle that defines all existence. When the last photon crosses the infinite dark, there will be no one left to see it. Yet that final flash will still mean something profound, that creation once burned, that existence once knew light. In the end, the universe may belong to shadow, but only because light once dared to shine. Thank you for joining us on this journey to the end of time. If you found this exploration of the cosmos as fascinating as we do, please consider liking this video and subscribing to our channel for more deep dives into the universe's greatest mysteries. We'll see you in the next one.